Share screen. The switching to iPad is sometimes weird. It asks me to install things from time to time. Okay, so last week we ended by giving a simplified formula for the directional derivative and for a scalar field. So not just for any function, but for a scalar field. We have this function f from a subset of Rn to R, and then we can define the directional derivative in the following manner. So it's given by this particular formula. So let's see this in an example. Let's see. Let's put it here. Great, that's not what I want. Let's see. So this is the formula that I want to use today for a problem. So this is my oops. Yeah, sometimes the machine takes over, sometimes I can control them anyway. So this is the problem. Find duf at this vector 3, -1, 0 for this scalar field. So this is my scalar field. Okay, so this is my function. Now this is just following this formula. So we need to find the gradient of f at this point, 3, -1, 0. So this is the gradient. So this is, I mean, it's just del f, del x, del f, del y, and del f, del z. So this is 4 minus 3zy square e to the 3xc. So this is del f, del x, then minus 2y e to the 3xc. So this is del f, del y. And finally, minus 3xy square e3xc. So this is del f, del c. Okay, so this is the gradient, and now at a particular point or a particular vector, oops, 3, -1, 0. So this is just plugging in the values. What we get is 4, 2, -9. And then from the formula, so so this is my u, vector u. So du, let's see, so just a moment. No, sorry. No, that's not u. U is something I need to give you. So this is the direction vector, 1, 4, So in this direction. Okay, so then du of f in this point, this is once again from this formula 1 over, well, norm of v. So in this example it was, or in this formula it was, the direction was given by v anyway. So this is norm of u. So the norm of u is simply the square root of 1 square plus 4 square plus 2 square. And then you take the dot product of this gradient with the vector. So 4, 2, minus 9, dot 1, 4, 2. So this is 1 over whatever it gives you, 4 plus 8 minus 18. So this is minus 6 over 20. So just an easy example of computing the directional derivative. Okay. So the rate of change of whatever you can say, the rate of change of the scalar field in the direction of u is negative, and the value is given by 6 over root 21. Okay, but the main point or the focus today, where did the point 142? Well, okay, so initially I didn't give you. So u is this direction. So you need to find the directional derivative in a particular direction. So yeah, this is the problem. So find the directional derivative in this particular direction. Okay, I mean that's something I didn't write down initially. Okay. Let's move the chat. Okay, but the main topic for today is vector fields. So what are vector fields? Vector fields are, the definition is very simple. So they are just functions, nothing else. They are just functions from a subset of Rn to Rn. That's it. Okay, so it's given by a bunch of functions. So f is, sorry, let's use capital F. So f is given by f1, f2, fn, where each fi are functions from x to r. Okay, so that's simply the definition. Some question, could you explain supposed to be? Yeah, so 6 over root over 21. So this number is the value, and the negative is, so it describes the rate of change of this function f, which is the scalar field, in the direction of the vector u. So whenever you find any kind of derivative, it's the rate of change of something, or rate of decay, or rate of increase, whatever the case might be. In this case, this is the rate of change of the scalar field in the direction u. The value is given by 6 over root over 21, and the minus sign shows that it's sort of decaying or decreasing. So that's the physical explanation of it. Okay, so depending on the situation. Okay, so what do we have here? So this is the definition of a vector field. Now let's see what vector field, more than the definition, the theoretical definition, the important thing is, what does a vector field give? So a vector field gives it gives a sense of direction. Okay, so in all cases, at least cases which we consider, the functions, this fi, so 1 less than or equal to I less than n, are infinitely let's probably, so they have partial derivatives of any order. Okay, or in other words, so this del L F I del X I L, let's see, maybe J is defined for any L greater than or equal to 1. So, or in other words, these functions fi, they're sufficiently nice or sufficiently smooth. So there are no, let's say, sharp curves anywhere in these functions. And so is the whole function f. So under that circumstances, a vector field, it gives a sense of direction to the n-dimensional plane Rn. Okay. So let's see examples to make things clearer. So define f from R2 to itself by the following formula: f of any vector is A, where A is fixed. Okay, so we pick a vector x and assign to it a fixed vector A. So that's my vector field. Now, if you draw pictures for this, it's in R2, so you can draw pictures. So what does it give? So this is the, let's say, x-axis, and this is the y-axis. Now, let's say this is my vector A. Then this vector field assigns this direction to the plane R2 in the direction of A. So every vector is given this direction A. Okay, so this is the picture of this vector field. Maybe I should. So this is my vector. So this is the picture for this function. Okay, so this is probably the easiest vector field one can draw. It's called the constant vector field. So F is called the constant vector field. Okay. Number one. Number two, now let's get to slightly complicated things. So define this vector field R2 to R2 once again. G of, so let any vector x have this coordinate x comma y. So G of x comma y is given by y comma minus x. Okay, so this is my function. So take a vector, then what does this do? So first you flip, right? So there are two operations hidden in here. So first you flip the coordinates y and x, and then you reflect along the y-axis, along the y-axis. So there are two operations. So first flip the coordinates xy to yx, and then reflect along the y-axis to go to this y comma minus x. Okay, but now if you want to draw pictures, then you have to get more information about this vector field. Namely, I mean, a priori these informations are not really apparent, but it can be figured out. So first thing is, so let xy be any vector in R2, okay? Then xy, if you take the dot product of xy with this vector field evaluated at xy, so what does this give? So this is xy times minus y comma x, so this is equal to minus xy plus xy, which is 0. So what does it mean? It means that the value of this vector field at each point or each vector is, or the direction it gives, is perpendicular to the vector, okay? So suppose this is my xy, then the direction of gxy is perpendicular. That's the first observation, okay? Then, so this is number one, let's see, observation number one. Number two is the following, that if you take the length, so if you take the norm of gxy, so what is the norm? So the norm is given by the norm of this vector. And from the definition, so this is minus y square plus x square. So this is x square plus y square, which is exactly the same as the norm of the vector xy. Okay, so the length of the vector, or the length of g of xy, is exactly same as the length of the vector. So the vector and its direction given by g has the same length. Okay, so with this two information, one can draw the picture. So what do you think the picture would be? So suppose you take a circle, let's say, and let's say this is the point x comma y. So where does this x comma y goes to? Exactly, that's the right answer. So I got a right answer. So that's all I can say, that they would be tangent to the circle in a counterclockwise direction. So this is g of xy, and similarly for any point, this is the direction. So you can take bigger and bigger circles, but the direction of the vector field would be exactly same, etc. So it rotates the plane R2. So G, oops. Okay, so that's the effect of the vector field. So it rotates G, rather it rotates R2 in a counterclockwise motion. So that's G is called, so obvious name, so G is called the rotational vector field. Okay, so it is this physical implementations of the vector fields which are more important than just the functions itself. Now, something from Newtonian mechanics. So define F from, now we take the space R3 and delete the origin. Okay, so this is my X, you could say, to R3 by the following function. So F of X comma Y comma Z is equal to C over three over two times the vector. So for so C is a non-zero scalar, so it's a real number. So F is called the inverse square vector field for the particular reason, which is follows. So let X be this vector, X comma Y comma Z. Then, as usual, the norm of X is given by the square root. Okay, so we can rewrite this as X square plus Y square plus Z square to the half. Now, with this notation, this vector field can be rewritten in this following way. So F of this vector X is C over X to the norm of X to the 3 over 2 times the vector X. Okay. Once again, this is same as C over norm of X square, the vector X over the norm. Okay, so it's just the way to write it or rewrite the initial expression. Now, this is the distance, right? Or this is the length of the vector X squared. So what it says is that, and notice also the other thing. So if you take the norm of X over this norm of X, the norm of X is a scalar, so you can bring this out. So this is 1 over norm of X times norm of X. So this is 1. So this vector here, so this is the unit vector in direction of the vector X. So in conclusion, what we can state is the following, that if the directions, let's say the direction so the direction of F is parallel. So that's all we can say, parallel to F of X is parallel to that of X, and if you take the length, whose length, so norm of F of X is C over norm of X squared, okay? this is inversely proportional to the square of the length of x. And that's where the inverse square vector field name comes from. Okay, so depending on this scalar c, you can guess that this vector field would be something called an attractive vector field or a repulsive vector field. So could you give me an example of attractive vector field which follows the inverse square law? Very famous example. Mass in space. So yeah, so this is where Newton comes in. So specific examples. So this is Newton's gravitational field. So what is the setup? So you have two bodies between two bodies of two bodies of masses, let's say m and m respectively. And typically, well, it's not really needed. I mean, but still, let's put it. The capital M denotes the larger mass. Then the Newton's law of attraction tells you this famous formula. So minus gmm by norm of x squared times x over norm of x. Okay. And this is perhaps Newton's most famous work. So C in this case is G minus GMM. So G is the gravitational constant. What's the name? Gravitational constant. Okay, so this is an example of an attractive vector field and perhaps Newton's best work. So this encompasses, I mean, this is where Newton's greatness lies, that it's not just that the gravitational force attracts a body. That's, I mean, that's an everyday occurrence, right? That apple falls from the tree to the ground or whatever. If you let something fly, it comes down. And that observation can be done by more or less intelligent people. So philosophers, maybe Greek philosophers, they all did this sort of philosophical observations that bodies, if thrown up, they comes down. So there is some sort of gravity, some sort of attraction from the earth. But what Newton's achievement is to capture that particular attraction in this mathematical formula. And it's not just between Earth and Moon, it's between any two bodies. So that's where his greatness lies, to encompass everything in this mathematical formula. Anyway, but that's something probably you already know from courses in physics. If you, I'm sure you have taken one. Now, what is an example of a repulsive vector field of this type, so which follows the inverse square law. Something which is equally important. So this one is an example of an attractive vector field. So what is an example of a repulsive one? Exactly. So magnets, electric charges, electric field, exactly. So that's the example I have in my notes also. So this is the, what's the name? So this is the electrostatic force. Between two charged particles. So maybe both positive or both negative. Then the Coulomb's law. So this is the Coulomb's law, which tells us that f of the vector x is given by k. Oh, this is actually what is called the Greek letter kappa. So or k, if you want, k, q1, q2 over the inverse square of the distance, of course, times the unit vector, where let's define the important things. So q1, q2 are the charges. Okay, and what else? This kappa is probably called the Coulomb's constant. Okay, so this is an example of a repulsive vector field. Okay, so we have sufficiently many examples of vector field to probably convince you that they're important in the sense that they occur in nature. So gravitational force and electrostatic force, they are probably the two most important forces that one can study in nature. What we are going to do later is to tie these vector fields with integration. So we want to find, so vector field, when they give this direction to planes. So imagine a body, for example, in this rotational vector field, imagine a body here. So this vector field gives it rotational direction. In other words, it does some work. So the vector field does some work in moving this body from, let's say, this position A to this position B. So we can compute the work done by this vector field. So this would be the topic which we will cover when doing integration. So we have vector fields. We want to know the work done by the vector field. So that will be the topic for integration. But for the moment, let's finish off with some definitions. We have defined the gradient of a scalar field before. Now, the divergence of a vector field F. So this is defined by, so the divergence of F is given by del F1, del X1. So it's the sum. Where this F is given by these functions F1 up to Fn. So this is the divergence. And one more definition, that of a curl. So F has three components, F1, F2, and F3. So in that case, you can define the curl. So the curl of F is defined as, imagine this vector determinant in some sense. So you have E1, E2, E3, which are the vectors, the unit vectors in R3. Then you have these operators, del x1, del x2, del x3. And now you have the components F1, F2, F3, and you find the determinant. So how do you interpret this determinant? In the following sense. So this is equal to, so del F3 del x2 minus del F2 del x3 E1, now minus del F3 del x1 minus del F1 del x3 E2, it's right here, plus del F2 del x1 minus del F1 del x2 E3. So it will give you a vector. So if you write down everything completely, this is the thing that you get. So this is del F3 del x2 minus del F2 del x3, the usual one, then del F1 del x3 minus del F3 del x1 del F2 del x1 minus del F1 del x2. So this is the form that, so the easiest way or the easier way to remember the curl is through this vector determinant type of formula. So this is not really, remember that this is not really a determinant, it's just a way to remember the formula, that's it. Okay, and now we have this beautiful results, which we state just as facts. So facts, for the second terms are the derivatives flipped. Yes, because we have a minus sign. So if you follow the definition of determinant, so there's a minus sign here. Yeah. So number one is the following, that the divergence of curl of F. So the curl of F gives you a vector field once again through these components. So you can take the divergence. So the divergence of curl of F is 0. And it's very easy to show, just take the derivative. So what is divergence? Divergence is the partial derivative. So you have to take the partial derivative with respect to this components, and if you add them up, you will get exactly this form. And number two is that if you take the curl of the gradient of a scalar field, that gives you the zero vector. So zero vector in R3. So we need the following condition whenever F is twice so in this case, F is a function from R3 to R. So it's a scalar field defined from R3 to R. So these are the two fundamental formulas, and in exams or in homeworks, not homeworks, but practice problems, whatever, I can ask you to show this sort of properties for specific functions. So you need to compute a bunch of derivatives and work a bit more to find these formulas or find these relations. So I'll give you specific functions, specific vector fields or specific scalar fields, and ask you to verify this sort of properties. Okay, now, so this finishes off with the second lecture note on vector fields, or rather on vector calculus. And we begin, let's see, the third note. So this is note 3 as per the eCampus note. Let's see, is it? I think it's vector calculus 3, something like that. Now, once again, the thing is that we shift to integration. So that's the main focus right now. And this note starts off with Riemann integration. So the definition of Riemann integration using these partitions and stuff. And once again, depending on what you want, I can just ignore the formal definition of Riemann integration and just state a few properties which we need, and then go over to the integrations that we need. That's one thing we can do if you are comfortable with Riemann integration, that is. So if you agree, then we can move a bit fast, or I can just start from the very beginning, whatever you prefer. So I guess move ahead, okay. Yeah, I mean, Riemann integration is pretty classical, so we can assume, or maybe I can assume that at least you can study them on your own a little bit. And I just want to state a few properties and then move on to line integrals. Okay, so what is the basic setup? So we have a function f from a comma b, so this interval a comma b to r, which is Riemann integrable, let's see. So Riemann. So it is Riemann integrable if it, so I would just say if it satisfies certain condition. So read the notes. And we use the notation integral a to b fx dx for the Riemann integration, the value of the Riemann integration, that is, or sometimes just f dx without emphasizing the x. So it satisfies a few properties, of course. And for example, if you take the sum of two Riemann integrable functions, is note 3, yeah, it's uploaded on eCampus, exactly, it's uploaded. So I think it's called VC3, if I'm not wrong. Let's see. Just a second. Up to VC2, really? Okay, proved. But I thought I uploaded. Maybe I forgot. Let's see. Oh, shoot. Yes. Sorry. This is my bad. Let me upload it. Yeah, so I'll upload it right now. Just name it integrals. Okay. Two, three, four. Okay, can you see now? It's called VC3 integrals. I hope this is the one. Let's just check. Yeah, good. Exactly. So this is the one we are starting off right now. Okay, so of course, it satisfies certain properties. For example, if you take two functions which are Riemann integrable, if you add them, it's still Riemann integrable, and the integration of the sum is the sum of the integration. Then if you multiply a Riemann integrable function with a scalar, then the scalar comes out. So these are some of the natural properties that that happens, or that if you take two functions f and g which are Riemann integrable, and then if you take the composition g composition with f, that is also Riemann integrable. The product is Riemann integrable. So these are things which happens quite naturally. Now, one property which I want to state here, and we are going to use it later, is on page 4. So if you go to page 4 of VC3, the last theorem. So this is something I want to state. Now, if a function, so facts, let's say number 1, so if it's integrable on AB, this interval AB, then it is also integrable on each subinterval. So you take any subinterval C comma D inside AB. And moreover, what is, whoa. What is more important is the following formula, that the integration from A to B of f can be broken up into two separate integrals. So you first integrate from A to C, and then integrate from C to B. Okay, so this is something, so keep this property in mind. We will use it while when doing problems in line integrals or vector integrals, whatever it is. But this property is something we will use frequently, because the main reason is that the function, the given function, or let's say given let's say a path in R2 or R3, it's not always smooth. So there are broken edges in a path. So we divide the integral keeping those broken edges in mind. So that's, I mean, that's where this particular property would be useful. Then again, this sort of things are not hard to show, that if f and g are integrable and the value of f is less than or equal to the value of g, then the value of the integral is also less than or equal to. The next property I'm going to emphasize is the fundamental theorem. So the fundamental theorem, it's on page 6. It says that suppose you have a function which is nice in the sense that f is continuous. Then you can define this capital F of x. So this is number 2. So this is fundamental theorem. I won't write the details. So f is continuous. Then you can define f of x to be the integral from a to x ft dt, where x is something in between a and b, okay? Such that if you take the derivative of f, it will give you the function f of x. So that's the, I mean, that's not exactly the fundamental theorem, that's one part. But the most important thing is that the second one, that if f is differentiable on this interval AB, then you can evaluate the integral of f prime by simply evaluating f at the endpoints and taking the difference. So that's the crucial result in fundamental theorem that we will use from time to time. And then the last one which I want to write down is the change of variable. So this is on page 7. So this is change of variable. Okay. So what does it say? That you have phi, which is continuously differentiable on a closed, let me write the terms, non-degenerate interval AB, okay? And f is continuous on phi of this interval AB, okay? So what does non-degenerate means? It's given in the lecture note. It simply means that A is not equal to B, and in fact, it's less than B. So it's a proper interval in that sense. Okay, so under this situation, we can evaluate this integral phi A to phi B. Now, here is the thing that phi A and phi B doesn't always give a non-degenerate interval. Even though A and B is a non-degenerate interval, there's no guarantee that phi A and phi B will give a non-degenerate interval. For that, you need special kind of functions. But anyway, let's write down this formula. So the integral of f in this interval phi A between phi A and phi B is given by the integral of f, this composition f of phi of x, phi prime x dx from A to B. In other words, this is integral from A to B, sorry, f of phi x d of phi x. So this is something which is, so what it says is that the integral doesn't depend on this change of variable. So whether you integrate f of phi x on this interval AB, or you integrate f on this interval phi of A to phi of B, the value remains unchanged. That's the most important thing. And that's what this change of variable formula tells you. Okay, so then there are these remarks which clarifies the situation. So let's put them as remarks. So it is possible, that phi of A can be greater than or equal to phi of B. But still we can make sense of this integral. So we can still make sense of dt by defining the following, that integral of c to d ft dt is minus integral d to c ft dt if c is greater than d. And then if c is equal to d, then the integral c to d, of course, is 0. I mean, if c is equal to d, then just from the definition of Riemann integration, you can show that the integral is 0. Now, the second remark is slightly technical and we will avoid this part, but I'll state it as it is stated in the note, that this function phi has to be what is called strictly monotone. So monotone means that if, for example, T1 is greater than T2, then phi of T1 is either greater than T2, phi of T1 is greater than phi of T2 for all such T1, T2, or phi of T1 is less than phi of T2 for all T1, T2. So that's what is called a strictly monotone function. And if phi is strictly monotone, then you can properly define this change of variable formula. But from the first part of the remark, we can show that without this strictly monotone assumption, you can make sense of this change of variable formula. Once again, this is slightly abstract. I'll just state here that phi needs to be strictly monotone in order that the integration is defined. But we are never going to use such technical details. So I would just say that it's given in the lecture notes. So let's stop today by defining what is called the scalar line integrals. So this is the first sort of integrals that we will consider, the line integrals. And so we are in page 8 of VC3. So line integrals are of two types. So the first one is the scalar line integral. Scalar means that we use the scalar fields to define the line integrals. And the second type is the vector line integrals. Of course, the name suggests that we use the vector fields to evaluate the line integrals. Okay, so what are the ingredients that we need? So let xt, so this is x1t up to xnt, from the interval AB to Rn be once continuously differentiable function. So this is the setup that we need. So a comma b, we take a less than b. So such functions So these are called the paths in Rn. Okay, so then once again, we define that a line tangent to this xt with this technical definition. So tangent to xt at t naught. So this is defined in the following manner. So t of t is given by xt naught plus t minus t naught x prime at t naught. So if you draw the picture, at least in R2, you'll see that this t evaluated at t is exactly the tangent at point t naught, or rather point x of t naught. So t of t is the tangent line at x of t naught. Tangent line to xt at x of t naught. Now, here's the first type of integral. So definition. For a path as above, of course, we define firstly the arc length. So the arc length element to be the following scalar. So you take the norm of the derivative of x and take this infinite or this infinitesimal element dt. So this is the infinitesimal arc length scalar. So x prime of t, the norm, this is given by the square root of x1 prime t square plus x2 prime t okay. So this is what the norm of x prime t is. Now the length of the path, so xt is defined from AB to Rn, is given by this formula L of xt, this integral a to b of this infinitesimal element. So this will give you the length. So this is the length of the curve, so length of the path. Okay, so this is the first type of integral that we'll consider. So this is a good point to end. So next class we define or we do some examples of computing this arc lengths, and then we move over to what are called the scalar line integrals and the vector line integrals. So that's the first type of integrals that we will consider. But for the moment today we stop here. A short class. So any questions? So I guess most of you know what's going on with this sort of things, the line integrals. Have you seen this in Cal 3 or even before Cal 2? I am not sure. Okay. So I guess the only new stuffs that you will learn maybe, or maybe not, I don't know, something called the Green's theorem, or if we have time, we go over to Stokes' theorem even, but depending on how far we cover. Yeah, exactly. So I think these stuffs are already done in Cal 3, but somehow this course, this course demands that we do it once again. I don't know why. Anyway, so if there are no more questions, then I think those were in Cal 3. Yeah, I think so too. Anyway, so if there are no more questions, then we stop here, and I will come back at 4. Okay, so have a good rest of the day and see you on Thursday then. Bye-bye.